Good evening, everyone. The topic that we are going to see now is reflection on a line not terminated in Z0. We already know from the general solution the equation for voltage and current of a transmission line. When a line is not terminated in Z0, or in other words, when the impedances are not matched, we say that reflection takes place. Only under proper matched condition, the total power or total signal gets transferred from source to load. So we're now going to see what will happen when the line is not properly matched. From the general solution, we have the two equations, equation 1 and equation 2, for current and voltage of a transmission line. When you observe these two equations, we can see that there are two components that are present. We have a plus S component over here and we have a minus S component over here. Once again, in current equation, we have a plus S component and a minus S component. The plus S component in the equations for current and voltage represents the incident wave, and the minus S component in the general equation represents the reflected wave. So any general equations of current and voltage contains two components, the component of the incident wave and the component of the reflected wave. So the incident wave increases or it varies exponentially with plus S. So it means it is an exponentially increasing, and the reflected wave, it exponentially decreases in amplitude with respect to distance. We know that S is the distance and this reflected wave exponentially decreases as the distance increases. In case of an infinite line, so infinite line is nothing but when the length of the line or when the distance is infinity, or in other words when the impedances are properly matched, we say that there will be no reflection. So when there is proper matching, there will be no reflection. When there is no proper matching or when the line is not terminated in Z0, there will be a reflected component of the wave. Let us now observe the reflected component. Now this equation contains two parts. The first part, as I said, this is the incident wave and this is the reflected wave. Similarly here, this is the incident component and this is the reflected component. So we will multiply with the two terms. This term represents, the first part multiplication represents the incident component, and similarly multiplying with the second part gives us the reflected component. So we will first analyze the incident voltage. So we are multiplying this outside term ER into ZR plus Z0 divided by 2ZR with the first term. So it is E power root of ZY into S. So we have multiplied with the first component and this is what we are obtaining. Now let us take ZR commonly outside from the numerator. So this becomes ER into ZR plus Z0 by ZR whole divided by 2ZR into E power root of ZY into S. So we can cancel out the ZR and ZR term over here and therefore we get ER into 1 plus Z0 by ZR divided by 2 into E power root of ZY into S. Let us have this as equation number 3. The reflected voltage component is multiplying with the second component in the bracket. Therefore, we get ER into ZR plus Z0 by 2ZR into, this is the second component, which is ZR minus Z0 into E power root of minus ZY into S. So we can cancel out this term and this term and therefore we get ER by 2ZR into ZR minus Z0 into E power minus root of ZY into S. We will take this ZR commonly outside. So it becomes ER by 2ZR. I am taking ZR commonly outside. So this becomes 1 minus Z0 by ZR into E power root of minus ZY into S. So this ZR and ZR can be cancelled and the reflected component is ER by 2 into 1 minus Z0 by ZR into E power minus root of ZY into S. So let us have this incident component or incident voltage as equation number 3. And we are having the reflected voltage as equation number 4. Now under open circuited conditions, we know that the impedance of the line will be infinity. So under open circuit, ZR will be infinite. So substitute ZR to be equal to infinity in equation number 3 and also ZR to be equal to infinity in equation number 4. So we know that anything by infinity, the answer is 0. So this total term will become 0. Similarly, this total term will become 0. So therefore, E1 will reduce to ER by 2 into e power root of zy into s. And similarly, E2 will reduce to ER by 2 e power minus root of zy into s. At the receiving end, so let us assume that a signal is transferring. This is the source point, this is the receiving point, and the signal is traveling here. When the measurements are made from the receiving end, this will be the starting point. Then if I make the measurements from here, so at the starting point the distance will be 0, because this is the starting point from where we are making the measurements. From here we will measure the various distances. So at the starting point distance will be 0. So therefore, substituting s is equal to 0 in the equations for E1 and E2, we will get e power 0 becomes infinity. So here also it is e power 0, and in the second term also it is e power 0. So e power 0 becomes equal to 1. So therefore, E1 will be equal to ER by 2 and E2 will also be equal to ER by 2. So these are the various conditions when the line is not terminated in Z0. Thank you.